Okay, folks, let's start then. Today we have Liz Flores-Rivera giving the PFITS Plus talk series this month. Liz is originally from Puerto Rico, where she also did her bachelor's in theoretical physics and minor in atmospheric sciences. After that, she did a master's at Cal State LA. That's actually where we met. And after that, she went to Europe then to do her PhD, which she did at the Max Planck Institute with Mario Floch. And she just finished her first postdoc in Copenhagen with Michiel Lamberts and Anders Johansen. And she's briefly back in Puerto Rico and soon going to her second postdoc in Japan, in Tokyo, with Yuri Aikawa. So, with no more further delays, we'll give the word to her. Liz, please take it away.
Thank you, Vlad, for that very nice introduction. And also thank you very much for inviting me to give a talk here in the FITS Online series. Indeed, today I'm going to talk about the vertical mixing and radial trapping of pebbles in protoplanetary disks. And two of the projects. This will be two of the projects I worked on during my first postdoc in Copenhagen. And by the way, you can feel free to go to my GitHub website, and in there you'll find videos, protoplanetary disk videos and particle motion videos that I will present here. But you can go there, click the download button, and use them if you will. All right. Well, protoplanetary disks, as we all know, they are not born in isolation, and they do not evolve in isolation. They are part of the star formation process in which we classify this process in different stages. So we have, for example, the class 0, where we have the young star that is born in this huge molecular cloud, is embedded in the molecular cloud, and this molecular cloud is spatially like 10,000 of AU approximately. It's huge. And interferometers like ALMA have observed already a couple of these class 0 sources. And so here I'm showing two of these class 0 sources observed in millimeter dust continuum emission by ALMA. And as you can see, these sources, you cannot really distinguish much of what emission is really coming from the disk. It's very smooth, blobby, and perhaps puffier compared to later on disks. And the puffiness, we don't understand yet whether it is shaped by turbulence or whether there's infall material also influencing it there. When we move on to the class 1, the disk becomes more visible, but we also have the presence of other features like outflow cavities. We have also the presence of jets. And we have this famous class 0 transitioning to class 1 source named the L1527, in which if we start from the right-hand side picture, this is the very famous James Webb Space Telescope image, is in infrared of the source. The two bright lobes corresponds to the outflow cavities of the source, and here's where we see the most detail of the source. We can see bow shocks, we can see hot bubble gases coming from the inner parts where the star is, and the inclination, the configuration of the source is edge-on. That's why we see this vertical lane in the middle, and it's also, as you can see, also is tilted 90 degrees. And on the right-hand side, sorry, on the left-hand side, I show a very low resolution image. It was taken from Spitzer, so the orange region, it corresponds to the emission that is traced by micron-sized particles, also from in the outflow. And over plotted, there's also the 12CO emission coming from the same region. And then in the counterpart is the emission from the N2H plus, which is tracing mostly the colder parts of these star formation regions, and this is material is infalling towards the star, and so on and so forth. And then when we move on to the class 2, we have most of this molecular cloud is dissipated. We're able to see the many features and structures of the protoplanetary disk where the planets are formed. And this is the very famous gallery from the D-Sharp ALMA large program that was published in 2018. You have probably seen this many times, and you're probably going to see it many times in the future too. But not all of these disks, they look the same, although they share very common features like systems of rings, gaps that we see in some of them. We see in some of them some spiral arms. We see in some of them some dust asymmetry. We see that some of them show very intense emission at the center, but some of them do show a dust depletion coming from the center. Some of them show even companions, and so on and so forth. Even though we don't really detect the planets that are forming here, we cannot discard the possibility that all of these morphologies that we see are solely they're not solely caused by planets. Maybe it's a combination of multiple processes. And here I'm showing the spatial distribution of the 12CO, the top panels for 5 different protoplanetary disks. And in the white rate squared, it shows the field of view of the dust continuum emission of their protoplanetary disk, which is shown in the top bottom panels. And so you can distinguish or compare the spatial distribution between the gas and the dust, which is incredibly large, which can tell us something about what sort of dominant processes are happening in different vertical layers in the disk. And so far, we have detected 4 protoplanets and in 2 protoplanetary disks. So the first one, which is the most popular one, is the PDS-70 disk, which was the first protoplanet was detected in infrared. And this is like on the left-hand side, you see the infrared image of the PDS-70 disk, and this blobby circle point source, almost like that you see here, is the PDS-70b. It's the first protoplanet detected ever. And then later on, a year after, it was also observed by ALMA at high resolution. And not only the emission from PDS-70b was detected, but also the emission of a second planet detected, PDS-70c, which is very close to the inner edge of the outer ring. And it was later confirmed that these are planets because there was emission from H alpha, which means that there's a lot of material that these planets are still accreting towards their center. And recently, we also found another planet, 2 more planets in this system WISPID, which was also first detected in infrared. And here you can see the point-like source planet inside the gap. And when it was observed by ALMA in high resolution, the emission of the planets were not detected. That's interesting. But instead, we see this very thin ring, which the people who did this study, they think that this shape of the ring is not necessarily caused by the planet, the outermost planet. The second one is actually detected in the inner parts of the disk. And here you see the confirmation of the H alpha emission of the outer planet. And then in the inner planet, they also confirmed later on. But all this is, it's been very interesting, although exciting. It raises also the question of what can these discoveries tell us about planet formation? We have to care about the protoplanetary disk. And although we don't understand exactly what causes these structures, it is important that the different wavelength regimes that we observe, they are actually probing different layers of the disk, which can provide us clue about what the radiation field is. And also when it comes to particles, so what can the particles height distribution can tell us about the vertical diffusion that could be produced perhaps by turbulence. And so all these things are very important for us to understand. So the most popular, let's say, solution about what could cause the structures in the disk are the planets. And it's obviously that the planets are forming the disk, but they might not be acting solely in shaping the structures and the morphology that we observed. And we can have the presence of instabilities, whether it's magnetic fields or whether it's hydro instabilities. But we can also have external factors like binary companions or late infall that could affect the morphology and the structure of the protoplanetary disk. And in today's talk, I'm going to talk about one type of instability in which, before introducing it, it's very fundamental that protoplanetary disks are essentially accretion disks. And people, when they first started trying to model protoplanetary disks, they came up first with what are the type of forces acting in the disk. So we obviously have the gravity, we have the pressure in both the vertical and in the radial. And in the radial, we have an extra term, which is the centrifugal force. And when you solve this system of equations, the solutions that came out are the density profile in terms of cylindrical coordinates and the rotational velocity profile in terms of cylindrical coordinate. And this was already derived by Nelson back in 2013. And once you have these equations, you can set it up in your favorite hydrodynamical code and then see what comes out. Now, there is a hydrodynamical criteria that says that the vertical profile of the rotational velocity is not constant over time. And therefore, we should see the production of some, or the generation of some vertical shear. And therefore, we have the vertical shear instability, which is mainly characterized by this upward and downward velocity perturbations. And here in this high resolution movie that I did during my PhD, each one of these lines will correspond to a gas parcel moving throughout the protoplanetary disk. And you can see they go up and down. We have some eddies and so on and so forth. Now, this vertical shear instability has gained a lot of attention in the last decade because not only might explain the angular momentum transport, but it can also explain the levels of turbulence, which is being found to be 10 to the minus 3, 10 to the minus 4 with cooling radiation, and which is very similar to the levels of turbulence that we observed with ALMA, And the limiting factor of the growth of this instability is that it operates in short thermal relaxation timescale. And the critical timescale here is like 10 to the minus 2. So meaning the gas has to cool very fast in order for the BSI to continue operating in the disk. And now there is a lot of question and ongoing research trying to investigate where in the disk can the BSI be very active. And that we can talk about later after the talk. And so here I put the vertical shear term, in which in terms of the varoclinic terms, it shows the change of in rotational velocity due to these pressure surfaces and these density surfaces that do not align with each other, and therefore the instability. Now, I personally do not do perturbational analysis throughout my career. I mostly use the vertical shear instability has a fact, it happens, and then I use it for my science case. So I use the vertical shear instability for my science application case. And so, for example, today I'm going to talk about, so the first talk will be the UV processing of the icy pebbles when they are influenced by the presence of vertical shear instability. And this is going to be in 2D configuration. And then the second part will be less about the chemistry and more about where these pebbles concentrate when we add another dimension, which is the azimuthal. And now, as a matter of motivation, we have UV processing signatures in our own solar system by studying the chondrite. So this chondrite that you see here is a CR, I think, chondrite. And the material that is inside this red circle is called a dark glass. And you can also spot it outside of the red circle in the chondrite, but tiny. And even though it's so pristine, it's the most pristine material that has ever been discovered in the solar system. And even though it's so pristine, that it still contains a UV processing signature because of this high fractionation in nitrogen, meaning that at some point during the solar system disk evolution, this material went through the nitrogen photodissociation region. It came back to the midplane to mix with other unaltered pebbles. And we also have UV processing signatures in with ALMA, for example, where through CN and HCN, where we think that these gases are probing the UV field. And with the James Webb Space Telescope, especially for edge on disk, when we look at the spectral, the flux, we can observe these absorption features that will correspond to particles that contain icy mantles. And these ices might not necessarily be composed of a single volatile, but might have mixed composition, which is a sign of thermal segregation. And I use this as a motivation to model the trajectory of the particles. And in the particles here in our simulation, we used Lagrangian particles. And the benefits of using Lagrangian particles is that each one of these particles have an ID, and so we can track their evolution over time individually. And we use two different dust particle sizes. So in gray, we use it's 100 micron sized particles, and in black, we have the 1 millimeter sized particles. And we include the gas friction, but we do not include the dust feedback. So meaning that the particles will feel the friction, the headwind from the gas, and they will lose angular momentum and they will move inward. So that's the inward radial drift. And so, yeah, and aside from the turbulence, the particle will also experience the settling initially, and then they will continue moving inward. Now, as a post-processing step, we use RADMC then to compute the dust temperature and the local radiation field from the TW hydrostellar template. So here you can see the dust temperature. And then on the other side, on the right-hand side, we see the local radiation field. And overplotted, there's 3 different vertical layers denoted by Z over R. And so here in our case, we use the Z over R equals to 0.2 to be the UV layer. So it will correspond to the bottommost layer of the UV radiation field. And this is the layer that we use for reference to calculate the level of processing of pebbles. And now here I'm showing the dynamical trajectory of the particles. So for 2 particles. So on the left-hand side, the 100 micron sized particles, and on the right-hand side, the 1 millimeter sized particle. And you can see at the beginning, they are settling towards the midplane, and after 40, 50 orbits, they feel the influence, the radial motion, but also the vertical motion of the vertical shear instability. And at some point, so for example, if we pay attention to the 100 micron sized particle movie, I also sketched the Z over R 0.2 layer. So you can see that at some point, the particle crosses the UV layer more than 1 time, so a couple of times. And so this information is what it will become important to then later analyze the level of processing of this particle that crosses the UV layer more than 1 time. So I'll tell you more later. Now, the idea that we did, we took at 50 AU, we took a bunch of particles. So that bunch of particle, it contains the particles from both sizes. And we found that 21% of those bunch of particles are 100 micron sized particle, all of them, and they cross the UV layer. Whereas the remainder, 79%, they have both 100 micron and also 1 millimeter particle that they do not cross, but all of the 1 millimeter particle size particle, they don't cross the UV layer. So they stay shielded in the midplane. But this doesn't tell us anything about what's the level of processing, of ice processing on this 100 micron sized particles. So for that, we have to take into consideration the chemistry. And so what we did is a very simple chemistry analysis where here we calculate based on the dust temperature and the local radiation field that we used at the beginning from RADMC. we were able to calculate the thermal desorption and the photodesorption and photodissociation. And for this figure that you see here, in particular, I'm showing the COI's destruction time in logarithmic scale and in units of million years. So meaning that the purple-most region will corresponds to the ice that will be destroyed within 1 year, which is super fast. So you can see because of that, the UV layer, the thermal desorption becomes very inefficient at 50 AU. But then photodesorption, photodissociation becomes somewhat relevant. And so we found out that for 50 AU at UV layer, the photodissociation process is more efficient than the photodesorption by a factor of 5. And we did the same analysis for water ice. So here, this is the concluding plot for the first part of the talk, where I'm showing the particle processing time in years in the y-axis, and in the x-axis, I'm showing the last crossing time, but in simulation orbits. Now, this information is important because this will tell us about the occurrence rate at which the particles crosses the C/R 0.2 at 50 AU. And so this is then the plot that I did here. So for example, a particle that had its last crossing time at 150 AU, 150 orbits, let's say this one, it will mean that it crossed before the UV layer like more than 10 times, like 13 times. Now, this is the factor I was telling at the beginning that then we use to calculate the level of ice processing by multiplying that factor with the orbital period of the particle and then get this processing time in years. And therefore, it also explains why the distribution of the particles that I'm showing here. So here, the horizontal dashed lines will correspond to the photodissociation time scale that I showed previously in the chemistry plots, purple contour plots at 50 AU, yes. And all the particles above that dashed line will correspond to particles that spend more than the time that the photodissociation takes to destroy the icy mantles of the particle, meaning that these particles will be processed when they come back to the midplane. Whereas the other particles below the horizontal dash line will correspond to particles that spent less time compared to the time that requires the photodissociation to destroy or remove the ice mantle of the particles. And so therefore I put the unprocessed. So 17% of the 100 micron-sized particles are the ones who will be processed and will come back to the midplane and will mix with other unaltered pebbles. Now, this is a fraction of a fraction, so maybe the VSI might not be an efficient mechanism to process the ices in the particles, maybe not. Maybe disc winds will become more relevant, which is a very interesting, let's say, statement, and I would like to continue investigate that. We follow up the analysis with by using an astrochemical code, which is Nautilus. Nautilus is a gas grain chemistry code, and it solves a bunch of like thousands of chemical reactions for hundreds of species. And so here we used it to try to investigate what are the chemical reactions the dominant chemical reactions when we turn on surface reactions, for example. So we did the first test. It's just let's turn off the surface reaction and absorption. And so we use one single particle for that. So the particle that I showed the movie at the beginning, the 100 micron particle that crosses the UV layer, that's the top right-hand side plot that you see. That's the dynamical track, spatial track. And then when we do that, we get this abundance profile at the bottom over time that shows like, yes, at the beginning, the particle is shielded. And then at some point when it crosses the UV layer, the UV photodissociation becomes the dominant chemical reaction. And then the particle loses the CO ice and water ice abundance. And then it comes back to the midplane like bare, basically. So we kind of did this to reconfirm that the previous analysis that I did with steady state chemistry was true. Now we did another test when we turn on the surface reaction, meaning that we allow solid species to react with each other in the grain. And we found out, sorry, that the OH ice, when it combines with CO ice, it produces CO2 ice plus H. And so when the particle crosses the UV layer, then the CO2 photodissociation reaction becomes dominant and it produces CO ice and O. So meaning that the CO ice abundance profile will be different from this one. It might not decrease, in other words, because CO2 photodissociation reaction becomes important, but it produces more CO ice in the grain. And then we did another test where we turn on the surface reaction and we include absorption. Absorption means that we allow now the grains to react with gas species. And in that case, the CO ice increases. The CO ice relative abundance profile increases when it returns to the midplane. Now, the question is, this might perhaps not be realistic because in the midplane, we expect that the CO gas is depleted. There's no CO gas, but instead it's in CO ice. So the question is, when does the recondensation of CO gas to CO ice happens in the disk and at what vertical height? So that's the question, and that's why we put there that there should not be absorption in the midplane. Anyway, we tried those tests. Now the second part of the talk, I will be talking about where these pebbles are concentrated in turbulent disks. So we have observed a couple of protoplanetary disks that shows contrast in the brightness distribution. And we think, I mean, it's pretty obvious, like they show that the particles are concentrated. If the brightness is intense, there's a lot of concentration of particles. This has only been identified in the submillimeter dust continuum emission. But for example, these two images that I'm showing here is for this system MWC 758, in which the top image is the dust continuum emission, and you see the dust two crescents. And when we look at the same system, but in scattered light, the dust crescents are not shown, but instead we see another type of feature, which are these two spiral arms. So the green contour, it shows the dust continuum contour of the dust crescent location. Now, in terms of statistics, I took this information from Jaihan Bai's PP7 chapter, where he did this statistical analysis. And he said that there's only 19 crescents observed so far in 13 disks, which means that more than one disk contains more than one dust crescent. And most of these disks, not all of them, but most of these disks are that they classify them as hosting dust crescents are low inclination disks. And we don't know necessarily, like these dust crescents do not have necessarily a case where there's a clear connection with a planet. We don't know how they originate, whether the planet is triggering them, or whether something else is. And the dust asymmetry origins, we think like the massive planet is the most popular theory, where we think that when a giant planet more than one Jupiter mass carves the gap, you have this viscosity transition between the gap and the part of the ring, but that doesn't have a gap, that excites the Rossby-Way instability, which is the responsible mechanism to create vortices in the gas. And if you have vortices in the gas, then you trap particles in the dust, and that therefore you see the dust crescent. That's the most perhaps plausible scenario. We also have binary companions carving an eccentric cavity, perhaps through the same process. And we can also have instabilities, whether it's MHD or infall motions or whatever, hydro instabilities that could originate the dust crescents. But in order to differentiate these mechanisms and understand the process of the dust trapping in vortices, then we study their gas dynamics also. And here I am showing the configuration of our disks with 3 particle sizes. The equation of state that we use is the beta cooling prescription, and here we use the time of 10 to the minus cooling time of 10 to the minus 4 of an orbital period. We use a low to moderate resolution of 37 cells per scale height in all directions, and these are these initial disk parameters that we use. Now here I'm showing a movie of the vorticity, the B-plane, and overplotted, I'm showing 2 different values of the dust to gas mass ratio of the calculated from the 1 millimeter particles at the midplane too, just to see where the particles are concentrated in our simulations. And by the way, in order to see in our simulations these vortices, it requires actually longer orbital time in order to see the fully development of the vortices. So that's why I'm showing here these the simulation orbits for 400 orbits and more. And the concentrations of particles actually happens inside of the vortices that we found to be one in the inner parts of the disk here and the other one that is in the outer parts of the disk, and some other concentrations in between, the shearing, sun flows. Then here I am showing the velocity profile of the particles inside the vortex for, on the left-hand side, the 1 millimeter particle, and for the right-hand side, the 100 micron-sized particle. And the top panel showing the vertical velocity, then the bottom, right below the radial velocity, the azimuthal perturbational velocity, and then the difference between the dust velocity and the gas velocity. And the thing is that when we look at this profile, the symmetry is basically broken. And not only that, but the vertical velocity, it becomes the dominant compared to the other zonal velocity. And because we think then that the vertical shear instability do not act necessarily directly to it's not the dominant mechanism that acts or that dictates the particle motion inside the vortex, then we think that if there's turbulence and if the particles collide, they won't collide at high speeds, which means that if they collide, they will be it will happen through sticking collisions, and then therefore it promotes dust growth inside these regions. And this is a comparison of the of the velocity profiles of the particle for this 1 millimeter particle outside of the vortex, and you can see this beautiful sinusoidal pattern that we expect to happen for the particle dominated by the VSI, but particle motion dominated by the VSI. Then here I'm showing the dust density distribution for these 3 different particle sizes, and you see all the traces, the outer parts, the outer vortex, and also some of them show they are tracing the inner vortex too. The 1 millimeter vortex. So the outer vortex in the 1 millimeter dust density distribution was only able to capture a fraction of the 1 millimeter particles, because since these particles drift faster compared to the smaller ones, the outer vortex was only able to capture a small fraction, because it also takes a lot of time for that outer vortex to generate it. And this is the vertical cross-section profile of the disk. And this is the dust to gas mass ratio in the midplane. This is the radial profile, of the dust to gas mass ratio, and for all the 3 particles. And the dotted line shows the initial profile, and then the solid ones shows the evolution of the particles. And we can see that there are some enhancements of the dust enhancement at the location where the vortices are, especially for the 1 millimeter and the 500 micron size particle. That this dust enhancement, if we consider a dust to gas mass ratio 0.01 and for a 1 millimeter particle, and with a Stokes number of almost 10 to the minus 2 in the midplane, then this can indicate that these are the favorable conditions for the streaming instability to operate. But then I'm not gonna say anymore because this is then out of my field. And then here I'm showing the dust scale height over time. And the dust scale height was calculated by, has the root mean square of the particle's vertical position, because with like random particles, you can also get this information. And we see that especially if we pay attention to the 1 millimeter size particle, we see these ups and down peaks and valleys that when we look at it in the dust continuum, in the dust density distribution, we see that it corresponds to these 1 millimeter particles being trapped in vortices. And these vortices are not symmetric with respect to the midplane. So you can see that for 424 orbits, the greatest concentration is actually below the midplane, but at some point it comes back up to the midplane and so on and so forth. And so the particles are influenced inside of the vortex, are mostly influenced by the vortex motion, but the vortex itself is still under the VSI influence. So the vortex will also tend to move up and down. And so that's why the peaks. And we were able also to calculate from this steering settling relation, the alpha Z. We were able to calculate this vertical steering for 1 millimeter size particles inside the vortex, and we found that this is about 3 times lower inside the vortex than if we would do the same thing, but for a particle outside of the vortex. Then we were able to generate synthetic images at different wavelength bands. So you see here at the top panels, you see the ALMA band 9, so lower wavelengths, and as we move to the right-hand side, we increase the wavelength band. And so we see that the greatest wavelength band, you see the emission is mostly dominated by the inner vortex, the inner ring, and the outer vortex is somewhat also bright. But when we go to lower wavelength bands, it's the distribution tends to be smoother. And when we convolve the images with a circular Gaussian beam of 12 AU, those many details that we observed before from the simulations are gone, but we still see the over brightness coming from the inner parts from the inner vortex in the ring, and not much from the outer vortex. So if we were to include noise in our images, probably we do not resolve the outer vortex. And not only that, but from this we cannot really observe spirals, and which are observed in the infrared images from ALMA. If we look at ALMA band 9 closer to more to the infrared images, wavelength, we do not see anything like that. And so these are the velocity residuals, so for different disk inclinations, and the arrows are pointing towards the location of the 2 large-scale vortices. And you can see that when for the location of especially the outer vortex, we see this red-blue line of sight velocity pattern that it corresponds to the deviations from the Keplerian motion around the vortices. So these velocity residuals means that you subtract the data from the simulation with a pure Keplerian model of the disk, and then you see these features. And when we convolve the images with a similar beam from the dust continuum emission, doesn't need to be the same beam, but I just did this toy test. Most of the very fine features are gone, it disappears, but most of the Keplerian deviation that we perhaps see is coming mostly from the outer vortex. Then here I just wanted to show these images from Lisa Wolfer from the ExoAlma. She published these velocity residuals from these 2 sources that host dust crescents, and you can see similar patterns regarding to this red-blue line of sight velocity Keplerian deviation around these dust crescents. We did the same thing, the same analysis, but with dust continuum, the dust continuum images. And here I'm tracing the black contour shows the 85% of the maximum brightness of the disk. And as we increase the disk inclination, we see that the elongation of the dust crescent also increases, which suggests that this projection, there's a projection effect that we might not we're not taking into consideration for highly inclined disks. And then here, this is the kinetic energy spectrum. So for disks that undergo not isotropic turbulence, you can see two different slopes from this kinetic energy spectrum. And so you have the Kolmogorov that has typically a slope of -5/3, which is indicative of this turbulent cascade moving forward. But it can also move downwards, so on the opposite side. And then you have the dissipation regime, the dissipation. So for BSI, which is not isotropic, this is a very characteristic pattern to see. And when we analyze the Rossby number, which was less than 0.1, and if it's minus 0.1, then this is indicative that the large scale motions in the simulations are mostly dominated. The kinetic energy is mostly dominated by these large scale motions in rotation motions in the disk. And then lastly, before finishing, I just wanted to bring this because this is what I was working during my visit in MPIA. So we are currently trying to correct for the gas temperature with photochemistry effects. And the way we're doing it is that we have a photochemical table from radiation hydrodynamical simulations from Ryo Nakatani, and where he solves the heatings and ionization rates in order to get these temperature, the temperature of the gas, and the electron abundance. And so with this, we implemented this in Pluto, and we corrected the gas temperature above a column density of 10 to the 22 particles per centimeter squared, which is like exactly where the gas temperature emission in this movie is showing. And so I wish I could tell you more about it, but this is very much a work in progress, and I haven't gone so far in it, but at least we were able to get it work. But it's just the analysis that we're still working on. So maybe perhaps it would be interesting to study the disk winds in here and see whether disk winds influences the particles motion above the disk surface and so on and so forth. But this is, very much work in progress. But anyway, I'll leave you my conclusion slide here, and I will be happy to take any questions.
Excellent. Thank you so much, Liz. Excellent work. Can I start here with a question from Orkan? He says he needs to leave early. Orkan, do you want to ask a question yourself or while you're still here?
Yeah, I'm still here. I gotta jet real quick. So hi. So Mike, that when you showed the spectrum, it looks like the energy is it's probably where you wrote the fastest VSI, and we've talked about this before.
Yeah.
It I'm going to suggest that the VSI mode is being forced right at the edge of what you're able to resolve properly, which is okay. But the fact that I see it looks -5/3 above that, it's really strongly suggests that your simulations are probably showing some inverse cascade taking place. This is what it looks like.
Yeah.
From the look of that. The way to test that is just look at the total energy, the kinetic energy. Are you seeing it slowly rise? Because we were also seeing that in the early days in the Nelson 2013 paper, that we were, when it was running long enough, we were starting to see a rise in the total kinetic energy, and then the simulation would break. And we were like, maybe it's because we didn't have enough resolution because of the flow of energy, but then we never followed up on it. And it looks like I'm seeing the same thing here. Did you ever look at the total energy? Yanni, the time series, say, of the globally integrated
Oh, okay.
pay.
No, no, no. I did some plots for different snapshots, but never for evolution. No. Like,
Do you still have that data set? Maybe
yeah,
we could,
yeah, yeah, of
maybe
course.
next week you're coming, right?
Unfortunately,
Oh, you're
no,
not coming.
because I
Oh,
just I just arrived to Puerto Rico and I've been suffering from jet lag. So
okay, no problem. But you will
but
participate, right? So
yes,
we can talk about it next week.
I'll be attending. Yes,
Okay, great.
online. Yes, of course. Yes.
And I'm sorry I have to leave. I have to go a little bit early. So, but
But
okay, great. Thank you very much.
great comment. I'm still interested on trying to better understand these kinetic energy spectrums situations because they're apparently a bit hard to interpret. But I'm all ears for you guys. Like,
Yeah, yeah, no, it'd be fun to talk about this some more.
Jamie
Okay.
has a question.
All right. See you.
thank
Bye,
you.
everyone.
Yeah. Um, great talk, Liz. That was lots of great work. If you could go back to part one, specifically the slide where you introduced the RadMC 3D when you're trying to compute the equilibrium temperature. So my question for this slide is, in your RadMC 3D setup, I'm assuming you're taking the dust density field, including the Lagrangian particles from that becomes your dust field, your opacity field, dust field for RadMC 3D. My question is, are you in that RadMC 3D calculation, are you accounting for any grains that are smaller than the 100 micron grains that you're tracking dynamically in your simulations? Like, are you accounting for any like micron or submicron size dust grains?
Yeah, very good question. Yes, I am considering smaller particles, smaller than the 100 micron size particles that I used in this case. So for
Hmm.
that, we used the approach from Roach from 2016,
Okay.
and where we use the dust size distribution defined based on this MRN
Yeah, MRN,
distribution
right.
with the power
Hmm.
law. And
Yeah.
so yes, we computed the dust density for these particle sizes by assigning like each grain size, and we used from zero point 0.1 micron to 30 microns, I think. So we
And
do.
then
Uh-huh.
and then is it like like a Gaussian distribution in the vertical direction for those grains?
Yeah, yes.
Okay.
I don't see much of the, I mean, I don't see actually difference between the dust temperature for each one of these small grains though. When I use
Yeah, yeah.
when I
No,
use
my question was more curious. Like, I'm glad you're accounting for that because my concern was that since your subsequent analysis is determining how frequent these grains are being exposed to the UV layer, but it's actually the smaller grains that is very opaque
Mhm.
to has a high opacity to those UV. So if you're not accounting for the fine grains and you're kind of like overestimating how much UV exposure that these grains might be getting, but it sounds like you're taking a more realistic, view of what the opacity field should look like. So I
Yeah.
think you're doing a good job there. Yeah, making sure that you're not like overestimating the UV exposure of those grains as they're getting, lofted up and so on. So
Yeah.
thanks for the yeah.
No problem. No problem.
Do you have other questions for Liz? Anyone? No? Oh, then I have a question. You mentioned that the vortex is not symmetric with respect to the midplane, because you said that the VSI does motions up and down. That comes as a surprise to me because the vortex supposed to be a Taylor-Proudman column, so it has a cylindrical symmetry, so it shouldn't have. I mean, it knows where the midplane is because of the gravity of the star, right?
Hmm.
But it doesn't have vertical structure. Um, I guess apart from the dust, right? So I guess I'm
Hmm.
going to say that it's not symmetrical with respect to the midplane. It's not the gas motion, but the dust motion. Is
Yeah,
that
yeah,
so?
exactly. I meant, yeah, exactly. Very good. I meant the dust distribution in this case of the 1 millimeter particle, just to explain these peaks in the dust scale from this
Mm,
plot. It's the dust distribution, not the vortex. Sorry. I'm sorry.
right. So what's happening is that you have the VSI motion on top of it, and then this VSI motion is then lifting the dust up and down.
Yes.
Right.
Yeah.
Another thing that would be interesting to measure to respect to that is how far up like the vortex motion go, because it's not seen in infrared, right? It's only seen in ALMA. I guess that with 100 micron grains, you're not going to see that. But if I had 1 micron grains or tracer grains, yeah, then
Oh,
yeah,
yeah.
you would be quite nice to know if I mean, if the simulations predicted that the 1 micron size grains would be seen, whereas in the observations we don't. Yeah.
Yeah, that's true. That's
Mhm.
true.
Yeah.
I think that would be very interesting, but yeah, it would be nice to investigate. Yeah.
Right. Awesome.
Yeah.
Oh, thank you very much. I will stop the recording now.
Okay.